Jefferson, the Virginian, and got 10 to the 75th dollars. Instead of log 27 bits per symbol, they were getting away with log 27 minus log of 10 to the 75th divided by 75, the appropriate base. The upshot is they were achieving a compression of 1.4 bits per symbol, not 4.7 bits per symbol. So they were getting a 3-to-1 data compression over random text. Now, who knows what the entropy was of that? You'd almost have to be the author, him or herself, to know what the true entropy of that was. And there's a delightful short story of 3 pages by Luis Borges, in which a person decides that he's going to write Cervantes' Don Quixote. Okay? So it wasn't enough for him to just copy Don Quixote down. He didn't want to do that. He wanted to become Cervantes so that Don Quixote was a necessary consequence. So he steeped himself in the life of Cervantes, the author, and went through many, many drafts. And at the end of his life, some 30 years later, he had finished 1 page, the first page of the novel Don Quixote. And there had been many X'd out versions and so on, but that first page was exactly the page that Cervantes wrote. So he was essentially causing P hat to equal P by experiencing the same life that Don Quixote did, to the best of his ability. Unfortunately, he died before page 2, and Cervantes, of course, of course, you don't think for a moment, do you, that an author, when he writes Don Quixote, is writing a zero entropy sequence with respect to himself. No, he's just as much in the dark about what he's going to write next as just about anyone, but less than anyone. I mean, good characters turn out to be bad, and things have to be revised, and on and on and on. So even an author is led on a stochastic trip when he writes the novel. Right. In summary, for arithmetic coding, all we need to do is to elicit conditional probability of what comes next from some person, and then have his identical twin, since he has the same thing, unravel it according to arithmetic coding, and you get a data compression to the entropy limit plus the distance from P to P hat. Now in practice, the estimator and his identical twin are computers. The computer then does a deterministic estimate of what P hat is next and lays out that amount of code space for the next few terms review. And the decoder takes the inverse of that. Right. All right, now I'd like to go back to the original question of what's the best data compression for a random variable x. Not many copies of x, just one outcome, x, drawn according to p of x. Just before his death, Huffman gave a short description of how he came upon Huffman coding. Huffman is optimal, minimum expected length code for a random, for a distribution P. Said he was in Fano's class, and Fano had said, if I could play the game of 20 questions, and I had something with probabilities P1, P2, P3, and P4, then probably I'd want my first question to be a one-bit question. So I'd find the pair of these or the three of them such that it divided the probability in half. And then I'd want the subsequent questions to cut it in half each time. But he couldn't prove much for that, and it wasn't optimal. See, he was greedy. He wanted bits right away, and it led him into traps, where all of a sudden you had a conditional probability of 0.99 versus 0.01, and now you have to use a whole bit to resolve that, and the entropy is essentially zero. So that was bad. So he mentioned in class, and Huffman was in class, it'd be interesting to know what the optimal procedure was. So Huffman said he went home and he looked at all codes of length 2. And so if you just have P1 and P2, the best you can do is assign a 0 and a 1 to these two events. And then he looked at all codes of length 3. Well, they're all essentially this. And obviously, you want the highest probability on the shortest sequence, P2 and P3. So then he went to all the codes of length 4. Now all of a sudden there are two interesting codes of length 4. This one where they have equal lengths, and this one where they don't have equal lengths. And so this is good for some P's, and this is good for some other P's. Then he went to codes of length 5. By now he's filling up pages. And codes of length 6, he was on the third page when all of a sudden he spotted what was going on. It is a greedy algorithm, but it's not greedy in bits. It's greedy in coalescing the probabilities. And so he was able to throw all those pages in the wastebasket, and then he went into class and he said how to do it. And the answer, Fano's response was, "Oh, is it really that simple?" Okay, so what is Huffman coding? Let us give some examples. P1, P2 through P sub m. And I'll look at, what should we do here? Let's put a 12, 6, 3, 1, 1 for these. 18, 21, 22, 23. This normalization isn't going to matter. Well, I'm going to make this a 4. And I'm going to forget the normalization. And that's that. Why am I making it 4? You'll see in a moment. Here's what you do. You combine the bottom 2 and add the probabilities up and carry the others over. But you reorder the list if need be. See, now here's 2 plus 3 is 5. Oh-ho. 4, 12. And then 5 plus 4 is 9. And this is 12. And then this combines into 21. So at each step, you take the bottom 2 probabilities, add them together, and form a new list with 1 fewer probability, still non-negative summing to 1. And keep doing that. Then this is the set of the tree for your code words. So here we go. 1, 0, 1, 0, 1, 0, 1, 0. Oh, even this turned out to be pretty degenerate. So this code word over here will be a 1.